Hey guys, I want to go ahead and start making some videos like what you're going to be watching during my maternity leave. You've already seen a couple of these if you've watched some of the videos that I've already had previously last semester, but I want us to just kind of get acquaintance to it. So I'm making videos again because I haven't made them for a year or so, and you're getting used to having them available on Canvas. Now, when I actually go out for maternity leave, which hopefully won't be for a few more weeks, you will have Mr. Christie showing these videos in class, and you will be following along and taking notes, and he'll pause and ask questions and review with you, and you'll have a chance to ask questions as well. So the beauty of this is you still have me as a resource, but you also have Mr. Christie, who is extraordinarily knowledgeable about everything chemistry, essentially. So you kind of have the best of both worlds. So what I want to do is focus on chemical equilibrium. This is hopefully the second unit of our second semester. We've already covered kinetics, and now we're going to be diving into equilibrium. So let's talk about what equilibrium is. Let's say we are doing a demo, and ideally we would have already done this demo in class, and hopefully we probably already have, but we're just going to kind of pretend like we haven't. What I want us to do is think about having two beakers. We're going to have a, let's say, 100 ml beaker. There we go, sorry. And a 400 ml beaker. And we're going to put 40 mils in the 100 ml beaker. And we're going to put 200 mils in the 400 ml beaker. And we're going to put food coloring in here, so we'll just make this red. And it can be whatever color we want it to be. Okay, and we're going to make some observations. And some basic observations we can make here is the fact that there's lower volume in the 100 ml beaker. There's more volume in the 400 ml beaker. The 400 milliliter beaker solution is red versus the 100 milliliter beaker is clear. And then the big thing I want us to focus on is the height level here. Now, of course, I can't draw. We know that. But if I had these beakers, like actual legitimate beakers, out in front of you, on the desk, you would see that the height, meaning the distance from the bottom to the top of the water, is going to be lower in the 100 ml beaker versus in the 400 ml beaker. And that's what I want us to focus on. Now, what we're going to do is we're going to take a straw and we're going to stick it in, okay, into both of these beakers, so one straw in each one. We're going to put our thumb on top of the straw, and we're going to basically capture the full height of that water, meaning let's say there's 2 inches in our 100 ml beaker, I should have 2 inches of water in my straw, and same whatever the 400 ml beaker is. And we're then going to take these straws and we're going to flip them. And we're going to take whatever content is in this straw and drop it into this beaker, and whatever content is in this straw and drop it in this beaker. And again, we're going to make some observations. Some of the observations we might make is that the 100 ml beaker is slowly turning kind of a pinky red color, whereas the red beaker is becoming a lighter red, and that's because if we think back to our Beer's Law idea, we are decreasing the concentration, therefore we are decreasing the amount of color we're going to be able to see, the red food coloring in particular. Now, from there, we're going to continuously do this. Back and forth, back and forth, back and forth, and eventually it's going to get really tiring and really old, and that's okay, because we're not going to do it forever. Now, some things I want you to notice as we are doing this back and forth, okay, is the height of the 100 milliliter beaker is going to increase. Why? Why is it going to increase? If we're taking water out of it, why is the height going to increase? Well, because we're adding more water to it than what we're taking out. If we think about the amount of height that the red is, let's say the red is 4 inches. And let's say this height is 2 inches. Here we're taking 2 inches out at a time, but we're putting in 4 inches. Therefore, we have a net gain of 2 inches every time we do this. Okay? Now, over here, what's going to happen to our water level? Well, it's going to decrease. Why? Because we're taking out 4 inches and we're adding 2 inches in every time. So we have a net loss of 2 inches here. And we're going to continuously doing this back and forth. And eventually, what's going to happen? This level is going to become equal to this level, meaning the amount of water we take in that straw is going to equal the amount of water we take up in this straw and transfer back and forth. Meaning, is there any net gain in the two beakers? No. If I'm transferring, let's say, I don't know, I'm making up numbers at this point, 3.25 inches from this beaker, I am also transferring 3.25 inches from this beaker. And we're going to continuously do that back and forth. But we're not going to see a net change anymore because we're transferring the same amount from here to here, and vice versa. That is actual equilibrium. Now, let's kind of translate this a little bit to chemical equilibrium. First off, let's say this is my reactants. And let's say these are my products. Okay, and as they are going back and forth, two things I want us to recognize here is we have reactants and products at the beginning of a reaction. This is a little bit different than we're used to. We're used to only having reactants. We're not used to having products as well. When we're dealing with equilibrium, equilibrium only occurs when both reactants and products are present at the same time. If there were no products present, what I want us to think about, let's just say we take all of this out, how many products are going to be turning into reactants? None, because there is none to be able to transfer. And then eventually, as we're turning reactants to products, we would be able to pick stuff up with a straw and transfer it back. So one of the things, again, I want us to recognize is that there are both reactants and products to begin with here. Now, the other thing I want us to recognize is reactants are turning into products, products are turning into reactants. This is called a reversible reaction, which is very important with equilibrium. If a reaction is not reversible, equilibrium cannot occur. Okay? Now, from there, what I want us to recognize is what equilibrium is. So let's look at that definition real quick. Equilibrium is when the rate of the forward reaction equals the rate of the reverse reaction. Okay, well, what is rate? Rate is what we just spent a good bit of time on in kinetics, which is the change in concentration over the change in time. So if we think back to what we just did, we had our clear reactants going to red products, and we also have red products turning into clear reactants. And this reversible arrow is our sign for equilibrium. Our chemical equilibrium is possible here. So reactants turning into products, products turning into reactants. Now, we had less of our clear and we had more of our red to begin with. So what does that mean in terms of rate? Remember, the factors that affect rate is collisions, the amount of collisions. Now, specifically, it is the average kinetic energy of those collisions being able to overcome activation energy, as well as them colliding with the right orientation. But let's just focus on the fact that molecules are colliding. If we have more, so a higher concentration, a higher molarity, what does that mean for the amount of collisions? That means they're going to be colliding more frequently, therefore there's a higher chance for a reaction to occur. So there's a higher chance for products to turn into reactants. Now, because there's less reactants to begin with, that means there's less probability for collisions, therefore a less probability for reactants to turn into products. So initially, what we would see is a high rate of products turning into reactants and a lower rate of reactants turning into products. But what eventually starts to happen here? As products are being used, their concentration is going to decrease. I'm sorry, I didn't mean to do all that, erase all that. This concentration is going to decrease. Well, as it decreases, what happens to the amount of collisions? They decrease as well. Therefore, the amount of products being able to turn into reactants is decreasing, meaning the rate of the reverse reaction is going to slow down, okay? Versus our reactants, as they're forming and we're increasing concentration over here, there's now going to be more of them, and they're going to start colliding more frequently, and therefore they're eventually going to start producing more products or produce products at a faster rate. So our rate is going to actually increase here. And eventually these rates are going to become equal, meaning the amount of reactants turning into products equals the amount of products turning into reactants. And that is what equilibrium is. Keep in mind, just like with our cups, if we actually go back and think about the beakers we were just talking about, the volume, the final volume in the two beakers will not be equal to each other. There's no way they can be. But the amount of volume that's being transferred is equal to each other. So equilibrium has nothing to do with the amount being equal. It has everything to do with the amount of transfer being equal. So that's very, very important here. Equilibrium does not mean the amount of reactants and products are equal, but it means the amount of reactants turning into products is equal to the amount of products turning into reactants. So on a surface level, it appears that the reaction has actually stopped. We don't see a change anymore. There's no net change that's visible. But if we were able to actually get on a molecular level, we would see that consistent change occurring. Okay, so if we kind of notice what's on the screen right now, this is our integrated rate law data like we saw in the last unit. So we have our concentration on our y-axis and our time on our x-axis, and we see a change in concentration over a change in time. What I want you to do is take a second, pause, and I want you to come up with some observations that you see based off of some of this data. Okay, so a couple things I want us to notice here is notice that reactants start up higher. Our initial concentration of reactants is very, very high, and our initial concentration of products is very, very low. So what does that tell us? It means actually products are zero, sorry. The amount of products turning into reactants will be none. There will be no products turning into reactants, but there will be reactants turning into products. And as we notice, that change begins to occur, and our reactants start decreasing in concentration. And notice what's also happening with our rate is this slope is becoming less and less steep, which means that change that's occurring is becoming less. It's the rate itself is going to be decreasing. Okay, as for our products, we have a pretty quick initial change because the amount of reactants turning into products is very, very high. But our initial products is low, and it slowly starts to increase, and we start seeing this rate increase, and then eventually it also starts leveling out. And notice what happens when it levels out. This is where our rate of change is equal to each other. And we can see that same type of effect here as well. It really doesn't matter how these lines are intersecting. The intersection of the lines or how the lines are set up has a lot to do with our initial concentrations as well as our stoichiometric values, which we'll look at in the next video. So hopefully that was a decent intro into chemical equilibrium, and that's it for right now. Thanks, guys.